Hello everyone. In this video, I'm going to introduce how to use the APIs in diffpy-cmi to do the customized PDF fitting. First, we import modules from the diffpy-cmi and numpy and sumpy and other basic Python libraries. We'll use it in the later sections. Before I do the fitting, I want to first make a basic introduction to the classes that we'll use in the fitting. The first class is a profile. The profile is an object to hold the data and metadata. For example, here we have a simulated dataset that is a linear line with the noise. And we create the profile called noisy linear and set x and y value in the profile. So how can we fit the data in the profile? We use a fit contribution object to hold all the information about each contribution in the fit. For example, a face in a multi-face fit and a model to fit it. So we create a particular instance of fit contribution for this noisy linear data and give it a short memorable name, NLC. diffpy-cmi also allows you to give this name attribute that we set to a noisy linear. Then we will give it noisy linear profile. And the NLC should contain the module to fit the data. The module can be defined by a string equation. For example, our data is a straight line. We want to use a multiply x plus b as a model. Here, the a and b are two scalar parameters, and x is an independent variable. This is the most strict way when we're using the diffpy-cmi. In general, a fit may contain multiple components, like multiple faces, but also constraints and variables and affect the fit. The object to contain the complex fit is the fit recipe, and we need to create a particular instance of this for our linear fit. Let's call it NLR for the noisy linear recipe. After instantiate, we add our contribution. After this is added, the fit contribution will be an attribute of the fit recipe, and the name of the attribute is the same as the name of the contribution. There's a default fit hook for the printing, which is not always useful, and we will clear it in this tutorial. And then we'll add the parameters from our fit contribution into the fit recipe using the add variable method. After you add the variable, you can access the variable in the fit recipe interface and set the value for the variable. Here we set all the value to be 1. Then we can start our optimization. The fit recipe is not in charge of the optimization of the parameters. It is only an interface to manage parameters and generate residue. We need to use optimization tools outside the diffpy-cmi. For example, the least squares in the sumpy optimization that was imported above with the name shortened to the least squares. To run it needs a computed residue and the variables and the values of those variables. So we apply the residual function to the least square and get the values of the initial value for the initial value and run the least square. After it's finished, the parameters a and b will be optimized, and we can plot the fitted curve, which is the orange one here. We get a very nice fit for this linear regression. We can also show the current value of the parameters using the fit recipe.show. So what if we have a more complicated example? For example, our data is a scaled and stretched zero-order Basel function. And you definitely cannot write a Basel function in a string equation here. So what we will do is that we define a Python function for this. We define a stretched and scaled Basel function, Basel x, a, and b, where x is the independent variable, a and b are scalar parameters in this function. And then we use register function to register this function we just defined into the fit contribution. And here we name it as f. And for the equation, we set it as f. Here's f is not a scalar parameter f, but a symbol that's representing the register function, Basel, we just defined. And then we're basically doing the same thing that we create feed recipe, create the hooks, add contribution, add variables, and set parameters, and set values for the parameters, and we run the least square. Great, we get a very nice fit of this stressed and scaled Basel function. So what if we have a more complicated example, which is our real-world example of PDF? Our model will include structures, of course, with those parameters like lattice constants and ADPs. And we can define our Python function for the calculation of PDF and add it to the feed contribution. However, every time there's a new structure, we need to define a new function, and this is definitely inefficient. We would like a Python class that can load the structure inside. So every time we just do load the structure, calculate its PDF, and then refine the parameters in this structure without defining new function. And diffpy-cmi provides the tools for that. And you must define the class as a child class of the profile generator. But usually users don't need to define it because diffpy-cmi provides a predefined PDF generator for users. But if you wanted to add a new profile generator, like for Raman spectrum or AMR spectrum, this is how you would do it. For this example of just PDF, we'll use add profile generator to add the PDF generator inside the feed contribution. After the PDF generator is added, it will become an attribute of the feed contribution. And the name of the attribute is the same as the name of the PDF generator. Here, I'll show how the PDF generator is actually used inside the feed contribution. The PDF generator is actually a calculator loaded with a structure here. And when you call this PDF generator, the PDF will be calculated according to the X value we'll provide for the calculator. And here shows the calculated PDF from the PDF generator we just defined. So in a nutshell, the diffpy-cmi basically is a modeling interface together with a library of PDF calculators and calculative functions. The interface for users to manage the variables and calculators are separated. Users need to combine them when using diffpy-cmi. This seems to produce a little bit more work because it's actually needs you to program more, but actually gives the opportunities to developers in the open source world to develop diffpy-cmi to do more and more things. And they can add new calculators in the library, keeping the interface untouched, use the calculators in another place, or develop their own interface based on diffpy-cmi. They can also build GUIs and other user interfaces that hide some of this complexity from the non-program users. In the next section, we'll show a simple example how to use diffpy-cmi to feed a single PDF. The PDF we choose is a PDF generated by a bunch of titanium oxide nanoparticles. And this is a file that holds our data. In this file, there will be the metadata in the header of the files, which has a format. The metadata key equals to metadata value. And follow the metadata header, there will be a 2 columns data. The first column is the distance of R, and the second column is the value of a PDF, G. And then we can guess our first initial structure we want to try in our modeling. But how can we guess that? By uploading the file to the structure mining app in the PDF ITC, we can automatically get a good starting model to save us some time. Here is the result from the PDF ITC, sorted from the best to the worst. And find the best candidate we can start with is a bronze phase with space group C2M. And this structure is from the materials project database. So we download the C file from the materials project database and save it here. Now we have a data file and our structure file. We can start our fitting. Let's create our first recipe. Of course, we can write a recipe just like we did in the last section. But here I want to present a more universal way and how to use a Python function to create a feed recipe from files. But before that, let me introduce this important function, create recipe I defined. The create recipe takes these arguments. The first argument is the equation I want to use for your model, just like what I show, like a multiplied x plus b in the former section. And the second argument is the crystals, which is a dictionary, the mapping from the name of the crystal structures to the crystal structure object. This will be used to create the PDF calculator in the equation. And next is the function, which is a mapping from the name of the function to the Python function, and also a list of the argument's name. This list of arguments name will be used to rename the name inside the Python function, because diffpy-cmi does not allow two variables with the same name. So many times you need to rename those arguments. And the profile is the data profile we introduced before. FC name is the name for the contribution inside the recipe. We name it as PDF. In this function, what we will do basically is create the feed recipe and then create the feed contribution. And for each of the crystal inside your crystal dictionary, you create the PDF generator with the name of that crystal and set the structure of the crystal inside the PDF generator and add this PDF generator into the feed contribution. And for each of the function inside your functions, you register the function inside your feed contribution with the name of the function and also rename the arguments of function with the arguments you provided. And then you set the equation for your feed contribution and set the data profile for the feed contribution. Here we name the x value in our data profile as r, y name as a g, and the standard deviation of the y as dg. And then we add this feed contribution into our feed recipe. We will get the feed recipe with the data and the models. But another thing is that currently we haven't added anything into our feed recipe. So we use the initialize recipe function to add the data into the, add a variable into the recipe. Basically, it contains two steps. First, for all the functions, for all the variables inside the function, we use this subfunction to add the variables inside the feed contribution. And for all the variable inside the feed PDF generator, we use this function to add it into the recipe. So let's look at these two sub-functions. First, to add the recipe, to add the parameters in the PDF generator, we use this function. There are many parameters you can add to the recipe, and how to add it is totally your freedom. Here we just represent a way that is commonly used when you try to feed the PDF of a multi-phase crystalline sample. We first get the name of the PDF generator, and first we'll add the scale factor inside the PDF generator. The scale factor is a factor you will multiply after you calculate the PDF. So the PDF is actually a scaled PDF calculated from the structure. And we give it a name according to our naming rules. You can also define your own naming rules. And we assign an initial value for it as 0, and we set it to be fixed at the start of the recipe. And then we also assign text on the variable. The text here means the label for the variable. One variable can have multiple labels, and the label will be used when you're trying to refine the parameters one by one. For example, if you have a lot of parameters, you don't want to type all the name of it, you can send them with the same tag and just type the name of tag to free the variable in the refinement. Here we use bound range to bound the lower range of the scale to be 0, which means the scale factor must be larger than the 0 in the refinement. We do the same thing for the delta 2 parameter. The delta 2 parameter is a parameter to the correction of a correlation motion inside your crystal. We also bound it as larger than 0. And then we want to add our lattice constant. Our lattice constant is living inside the lattice pair attribute inside the SG pair attributes of the phase attributes of the PDF generator. Here, for each of the lattice constant pair, we add it to the recipe. You don't need to worry about symmetry because the lattice pair has already been constrained by the symmetry of your structure. And then we want to add our ADP. And ADP is an attribute of atoms inside your structure. To get the atoms, we use the getScatters method in the phase attribute of the PDF generator. you will get a list of atom object. And for each of the atom object in this list, we get the attribute biso, which is the isotropic displacement parameter for these atoms, and we add it to our recipe. And for each of the x, y, z position of the atoms, we also get it from the x, y, z pairs, from the SG pairs of the face attribute of the PDF generator, and add it to the recipe. It's also like lattice constants. They are also constrained by the symmetry, so you don't need to worry about the symmetry constraint for the x, y, z. Also, these atoms are also the symmetric equivalent atoms, so also don't need to worry about the symmetry here. Next, we'll introduce how to add our parameters in the fit contribution in the fit recipe. Those parameters in the fit contribution is actually the parameters from our Python functions. So basically, we just need to provide the name of the parameters, get it from the fit contributions, and add it. It's pretty simple. So by using these two functions in initialized recipe, we can add those variables and constrain those variables in the fit contribution and add them into the fit recipes. Here we write our final main function, which is to create recipes from files. Basically, we want to load up structures from the C files and want to load up data from the data file. What it do basically, it will first load all the structures from the C files and give it to the dictionary of crystals. And then we use the PDF parser, which is defined in diffpy-cmi, to pass the data in the data file, and then load the data in the parser into the data profile. At the same time, we'll also update the metadata in our profile if we have additional metadata, which is not recorded in the data file. And then we use the create recipe we defined before to create a recipe, using the crystals and the data profile and other arguments. And then we use the initialize recipe method we defined before to initialize the recipe. So we will get the recipe with all the models and variables prepared. So let's use it for our first fit. If you remembered, our first fit is actually a single phase fit of a bronze phase. And because they are nanoparticles, we are using a characteristic function to damp the PDF to simulate the finite size effect. The characteristic function we choose is a spherical characteristic function, which symbolizes a particle with a sphere, and it has a diameter of bronze size here. So our model is sphere multiplied by bronze. The sphere here is a spherical characteristic function with the parameter r, which is an independent variable, and the parameter bronze size. And our bronze phase is a PDF calculated from the structure in the zip file we downloaded before. Here we also provide our data file, which is gr file, and also we have additional metadata qdamp and qbroad, which is gotten from the calibration. And here we'll show the status of fit recipe. The first section of the status will be the parameters in our fit recipe. You will already find that all the parameters related to your bronze phase are added into this recipe now. Okay, now we want to optimize the parameters in our fit recipe. In the last section, we have already shown how to do that. And here we just made a function to do that, so we can set the parameter for a little bit more functionality. Basically, we want to refine those parameters step by step. And then also we want to set the refined range of data from rmin to rmax with the interval for r step. Here is how it is used. Basically, we want to refine our recipe, and we want to first free the scale of the bronze and the lattice of the bronze and refine it. After they're refined, we free our ADP and delta2 and refine again. Then we free our XYZ, and then we free our size of the particle. For the refinement, we'll do in a shorter range at the beginning, from 1.6 to 20, with a step size of 0.02, and our tolerance for our cost function will be 10 to the minus 4 power. Here we visualize the fit. after we optimize the recipe. We are using the matplotlib to visualize fit. It's not necessary to go into too much detail for that. You can also use your favorite plotting software to visualize it. And here we have our fits. It looks good. And then we'll save our data in the files. And I haven't introduced it how to do it before. So I'll go to the details of this save result function. It takes the argument of the fit recipe and then directory where we want to output the files, and the file name to save those files. And also, if you want to save the structures, please provide the list of name of the PDF generator you want to save. And here is the function, how the function is defined. Basically, first we'll make the directory if not it doesn't exist, and then we'll get the path to those files. And then is the important step. We use the fit results class in the diffpy-cmi to generate the fit result from the recipe. And we use the save results method in the fit result class to save the result in a file here. Important thing is that this save result will only save the refined parameters. But what if you want to save the fitted data at the same time? We need to get the fit contribution from the recipe and get the profile of it. And then we use the save text method in the profile class to save those fitted curve inside the data file. So what if we also want to save the refined bronze structure? So for each of the PDF calculator, we'll get the calculator from the fit contribution, and we get the structure from the structure attribute of the PDF calculator. And then we'll use the save output method inside the structure class to output the data in the structure into a file. So we'll use this function on the fit recipe we refined before, and we'll get three files: the CIF file, a FGR file, and a RES file. The RES file is a text file of the fitted result. You can see the goodness of fit in the file. Also, you can see the value of the refined parameters and the standard deviation of it. You can also see those correlation between the parameters. And the FGR file is the fitted file. Is the fitted data you save from your profile. It's a 4-column data file with X, calculated value of Y, data Y, and standard deviation of Y. And the C file is the C file of the refined structure of bronze here. Okay, we have gone through the whole process of the fitting, and we probably want to improve our fit. And we guess that there may be an impurity phase in our data. But what is this impurity phase? So we use PDF-ITC again to find the secondary phase. We export the residues here from our file. And then we upload it to the PDF-ITC, and we'll get our search result for the residual curve. And PDF-ITC tells that our residual curve probably contains another titanium oxide structure, which is the annotate phase. So we download the structure from database here. And then we'll build a two-phase model to feed our data. To build a two-phase model is no different from building a one-phase model. We just need to change our equation. We use a spherical 1 function to represent one spherical characteristic function, and spherical 2 to represent another characteristic function. Of course, they should have different parameter name. And then we use these two functions to damp the two phase. One phase is bronze, is calculated from the CIF file before, and another phase is annotate. This PDF is calculated from the CIF file we just downloaded. One important thing here is that we want to use the refined parameters from the last fit as the starting parameter for this fit. So how can we do that? We use the initialized recipe method in the diffpy-cmi to initialize the parameter in our recipe using the values in the data file we just saved in the folder. And then we will run our optimization function to optimize the parameters. And we can look at the fit again. It looks better than before. So we save our data, But we're not quite totally satisfied with the fit, because in the residual, we can still see a slow varying trend inside the residual. So what is it? From our collaborators, we know that they add some organic ligands inside our samples, and these organic ligands may produce a slow varying PDF inside our signal. But we don't really want to fit the structure of them because it's not important for our scientific project. What we will demonstrate that we can actually build an analytic function which simulates this kind of PDF we're not care about and remove it from the signal. And then we get a much more accurate fit for Brown's phase and annotate's phase. Here we approximate the PDF of the ligands with the Gaussian damped sinusoidal wave. And we define a Python function for this wave. The Python function contains the independent variable r and 4 parameters a, s, k, r0. And then we just need to add this function in our model. It's very simple. We just need to add the ligands as a symbol in our equation. And also we notify that this ligand is a ligand function we just defined before. And we name our arguments with this. And then we can use the initialize recipe to initialize the parameters in the Brown's and annotates using the parameters we just get from the last refinement. And also we need to set initial parameters for our ligands function. And then we can start our optimization again, and we can get a better fit. And here we save our fit in another folder. Okay, so we are basically satisfied with this fit in the small range. We're going to extend our fit into a longer range. It's actually very simple. We just need to change the Rmax value in the optimized parameters function, and the other part is the same as the last fitting. And then we can get a fit for the whole range. There's a problem. If we look at the higher range from 30 to 50, we'll find that the PDF of calculated value, which is the red curve here, looks like it's over-damped compared with the data curve, which is the blue curve here. So we guess that we may use a not so accurate characteristic function. So we want to change our characteristic function to try different possibilities of the size and shape of our nanoparticles. How can we do that? Basically, we just need to change the function. Okay, make our first hypothesis. We assume that our nanoparticle is not sphere. It's actually a co-shell model where the Brown's phase is the core of the nanoparticle, and the annotate's phase wraps the core of Brown's phase in the spherical particle. So it's a shell. How to use that? How to make the model like that? Basically, we make an equation like this. We use the characteristic function core for the Brown's and characteristic function shell for the annotate. And the core is the same as before because it's a spherical characteristic function. And the shell will be a shell characteristic function for the annotate. The shell characteristic function has the parameter of the inner radius and the parameter of the thickness of the shell. Basically, we do the same thing as we did before. One important thing here is that the diameter of the core should be equals to 2 times the inner radius of the shell. To do this, we use the constraint method in the fit recipe. In this way, in our refinement, the diameter of the core will always be equal to the 2 times the radius of the shell. It will be determined by the 2 times the radius of the shell. So we don't need to worry that they are different, and there could be an accurate co-shell model. We do the refinement again, and we visualize the fit and compare it with the spherical function. Sadly, it doesn't improve the fit that much. The spherical and the co-shell model are basically generate a similar PDF. So let's try another characteristic function. Maybe our nanoparticles is actually not a sphere, but a spheroid. We also have a characteristic function which is predefined of diffpy-cmi for the spheroid, and we use it in our fitting. It has 2 parameters, which is the radius of equator and radius of polarization. we basically doing the same thing of the fit, and then we get a better fit of the spheroid. Okay, maybe our shape of the particle could be not a spherical, but a spheroid. But there could be other possibilities. For example, maybe our nanoparticles are not the same size. They have a distribution of their size. And here, the the diffpy-cmi provides a calculated function to simulate the case where your particle are spheres and the size of spheres follow a log-normal distribution function. And its parameter is the mean value of your log-normal distribution and the standard deviation of your log-normal distribution. Here we also do the same thing for the fitting. It's exactly the same as we did before, and we can compare the result from a former fit. Basically, the log-normal distribution function generates a very similar effect as a spheroid characteristic function. It's hard to distinguish these two effects. So we have demonstrated how to use different characteristic functions for our PDF fitting. This is basically the end of our tutorial. Before I make a summary, I want to notify one other thing is that when you use the characteristic function in the diffpy-cmi to fit the particle size and compare it to the TM result you get, you will always find that it will be always smaller in the TM result. But don't worry, it's not that PDF diffpy-cmi is not accurate. This is because the particle size defining the characteristic function is actually the size of the domain of the structural order, and this will be always smaller than the physical size of the particle you saw in the TM result. So here we make a summary. By our fitting, what conclusion we can get? We can get that our titanium oxide nanoparticle actually contains bronze and anatase phase, where the bronze phase is a majority and the anatase phase is a minority. And the anatase phase probably occupies 9% of the total nanoparticles. And the size of the bronze phase is for about 50, and the size of the anatase phase is about 70. And the parameters of the bronze phase and anatase phase is shown in the fitting result below. So, in a summary, in this tutorial, we have introduced a universal way to build models to fit the PDF data using the diffpy-cmi. The users can not only use any characteristic functions and structures in their models, but also define their own calculators as the Python functions and refine the parameters in it. It offers the user the freedom to create and refine models beyond the traditional ways of multi-phase modeling, where the PDF can only be calculated by the structures and the limited number of predefined characteristic functions. Thank you for watching.